good to go. So again, Aviral, it's like a tutorial that students in the group are giving on adversarial robustness. Feel free to ask questions, jump in whenever you want. So there's no restriction on that. So, it's an open discussion. But the whole idea is everybody knows this new topic of research. Okay.
So today we'll be picking up where we left off last week from adversarial attacks. So last week we were looking at targeted, both targeted and untargeted FGSM attack, or fast gradient sign method attack. And we were looking at our optimization problem. And this was our goal. Oops, my bad. So this was our goal. We wanted a perturbation eta to add to our point X, and we reached the target label, which would be a misclassification. And that was our goal as an attacker. And we saw that it was very difficult to optimize for this function. So we replaced it with a softer, this is a hard constraint. So we replaced it with a softer constraint, this objective function, where we said if this objective function is less than 0, then our this function holds true. We also looked at how optimizing for our p-norm of eta was challenging. We replaced that with a proxy function, which involved the sum of the terms of our perturbation eta, and where what was remaining was our resulting adversarial example, and we will be talking about that today. So we want our example to be within a certain range. There are usually multiple constraints, but let's consider this for this instance. For example, if we were dealing with the MNIST data set, we would want our perturbation to be within 0 to 1 pixels. So we want a misclassification, but we don't want that attack to be too obvious. So if it's in terms of pixels and an image data set, it would be too distorted. So this function we can also, if given x is a constant, we can rewrite as eta is between negative xi and 1 minus negative xi, so two ends of our bounds. So for example, it would be like this, if this is our point, and we have this, sorry, excuse my drawing. This would be our bounding region. And let's say this would be our x, this would be our xi minus xi. And this would be 1 minus xi. So two ends of the bound. And and so this is where the optimizers come in. So how do we make sure our eta is within this range? There are two options. One is the LPFGS B optimizer. The B here stands for box. And we pass in our eta, and we just get our corresponding range, corresponding value. And another method is the projected gradient descent, or PGD. And what PGD does is, say you get your eta to be somewhere outside the box here, and we project it back to the box. So say our eta is less than x minus 1, so less than minus xi, so somewhere here, and we project it back to the surface, closest surface at xi, negative xi, which would be this. If our eta is already within our box, within the range of our box, we just let it be. It remains as it is when it is within the box. And when it's more than our 1 minus xi, so let's say somewhere here, we again project it to this part of the bound, this end of the bound. So this process is called projecting, and we clip our eta to the values here, and we project it back within the bounds, so we don't get too much of a distorted, let's say, adversarial example. And we want to minimize our perturbation. So as I earlier mentioned, we've
Taif,
so far,
Taif, can you go back to the previous slide?
sure.
So when you're in the PGD attack, basically what you're saying is, given a pixel and a perturbation, you check the perturbation value and see if it is beyond 0 and 1,
Oh no, no. So this is a constraint,
right?
and we have this bounding, and we want our adversarial example to be within this hard constraint, within this bound. And there could be multiple constraints. This is just one constraint, and we project it within that bound.
Mhm.
So is that could you repeat your
Okay,
question?
I get it. Okay, I see what you mean. Okay,
So we will see a whole example, and it will be more clear.
okay, good.
So yeah, we will now look more deeply into our PGD attack. We looked at FGSM, and FGSM PGD is just FGSM with projection, iterative with projection, and this is very commonly used for adversarial training our network to be more robust. So let's illustrate a PGD attack. We're given a data set of points x, y, and our label is 0 and 1. So if x squared plus y squared is less than 16, then our property holds, so it's 0. And if otherwise our property does not hold, then it is 1. And we create a neural network to classify these points. So this would be our graph. Everything inside the graph, the property holds, and everything outside the graph, the property does not hold. It's 1. So this is our, after creating the neural network, the classifier, this is what we get. This would be our decision boundary. The dark blue is where the property does not hold, and light blue is where the property does hold. And that's what the neural network believes. And these points, the red points, means the property actually holds when neural network predicts its holds, and the white points are when it doesn't hold. So for example, here the neural network thinks the property does hold because it is in the light blue area, but it's a white dot, so it means the property does not actually hold there. Another example would be uh, here the neural network thinks the property holds, and the property does actually hold here because it's a red dot, so the property holds. So let's look into this further. So let's say we choose a point uh, and are under L infinity ball. So L infinity bond would again be a range. It would be this range, this box range, and our epsilon, which is the radius of this box, uh, is our L infinity ball radius. And we pick a point, these 2 points, and let's zoom into the point. So this is our original x orange, and we try to pick a point near the corner. So we want to illustrate our projection. It could have been any other point, and necessarily it wouldn't need projection. So to illustrate our projection, we're taking this like specific point, and this would be the coordinates. So we take our points, which we saw in the previous slide, these points, and we run it through a neural network. And we notice the neural network classifies that the property actually holds, and the property actually does hold because it's white and it's in the light blue region. We can compute a loss, and we compute the gradient of the loss. We looked at this last week. So here we use our loss gradient of our loss to compute our x prime. So this would be our initial perturbation. So last week we saw that if the sign of the gradient is less than 0, we will take it as -1. And if it's 0, we take it as 0. If our gradient is more than 0, we take it as 1. So for this instance, both the values are negative. So we will get -1 for both of them here. And resulting value would be -1.9 and -2.7. So we use the x here, the values here. We multiply -1 with 0.1, and we add our previous x, and these are the points we come up with. This is the yellow point. So as we can see, this is outside our box, and we want to project it back to the box because that's our constraint. We want it within this range. This is our L infinity ball. We project it back, and using our projection function, these are the coordinates we get. This is the new projected point, and we notice that this is within the property holds decision boundary of our neural network. So we run our point through the neural network, and the neural network classifies that the property does hold. So this is not yet a counterexample because the property does hold, and we want a misclassification as we're making an attack. So we repeat the process. It's an iterative process. This is our second iteration. We repeat the process. So x double prime from the last slide is x now. And we again do the same thing. We have two negative sign values, similar calculations as we saw previously, and we come up with this x prime, which is again outside the box, and we want to project it back inside the box. And we perform our projection function, and we project it back, and these are the coordinates we get. And we notice that it seems like this is in the dark blue region, and this might be useful for us as we want a misclassification. And we run our point through the neural network again, and we notice that uh, the neural network does misclassify it and thinks the property uh, does not does not hold. But the property actually holds uh, because if you put in these values in our initial equation that we use to get our graph, that this value would end up being somewhere around 10. And if it's less than 16, it should have been classified as the property holds. It should have been classified as 0. So this is a example of the PGD attack. It happens in usually a predefined number of iterations. So with this approach, this is what we get. This is our target label, and this was the initial label. So if with slight perturbations, we can make the neural network think that it's the target label is 1. With more, we can make it think that the target label is 2, and so on and so forth. And here we can see that to the human eye, these look very similar, and we can't really tell much of a difference. But this is more particular to MNIST data set. This is very easy to attack. Um, it's very easy to fool the neural network. So some notes on PGD. PGD maximizes loss. It finds a point in that region which maximizes the loss. For our example, we started at the corner, but it usually chooses random point, and if it's inside that box, we don't need any projections, and it usually requires a predefined number of iterations, so we hard code it, and and there are two ways we can implement PGD. So we can project the current point with multiple constraints. One is within the, say, L infinity ball region with epsilon epsilon radius, and also within the range of the pixels. For example, we don't want it more than between each dimension between more than 0 to 1 pixels. We can also do it, uh, uh, make the change between negative epsilon and positive epsilon, and as well as add more constraints, such as the point being uh, this between this range of pixels, for example, of uh, uh, image data set. So yeah, that was our PGD attack, and now we will be looking at adversarial defenses.
Yeah, so basically, let me just stop at this point, just
Sure.
for everyone. Basically, so far what we have been looking at, what Abhijit and Taif talked about, is basically attacks. So attacks are adversarial attacks are basically some sort of changes that one can do on an input image or an input data point, so that you can fool the network. So far we haven't looked at any of, how can you now prevent the model from being fooled. So far the whole idea was, how can you get an attack that is accurate and smart. And that's why we, like FGSM and PGD, all of them were doing some sort of optimization, trying to change some values in the input data by a small degree, so that the network gets full. And there were strategies around doing that, and we saw that at least most of the both of the attacks that we saw use some sort of an optimization problem to solve, that's being solved to get that adversarial sample point. And these are interesting because the adversarial sample points, you can imagine that even in, like, images are still very, I would say, something that you can visually see, but they can be more difficult to observe in data sets that we actually cannot visualize. And it makes it very, very challenging for the networks to be able to, detect and defend against those. So the whole notion, there's a whole, like, research around developing these attacks, and there is obviously a ton of work around that and still going on. But more critical becomes, as these attacks are coming up, is can we prevent and, create defenses against those attacks. And when we say defenses, that means, can we have something, you know uh, in the model architectural design, or some sort of pre-processing steps that will prevent your model from being fooled. And that's what I think we are going to talk now in the adversarial defense part of the lecture. Any questions, anyone? If some things were overwhelming, it's, we need to revisit them again. But the point is, you at least get a sense of what we are dealing with. But yeah, if there are some things that it's still not clear, please, you could either stop at the moment, or we can always come back to it whenever we want to. These are still informal discussions, but we can keep coming back to it. If there are no
Yeah,
more
please.
questions. Yeah, there is a question.
Oh, awesome.
Is somebody? No. Okay, if there's no question, then let's continue, Taif.
Sure. Yeah. Please feel free to stop me if there's any question, if any more clarification. Yeah, please. So yeah, let's start with adversarial defenses. So first, we should define the term adversarial accuracy. I think most of us are probably familiar with test accuracy, but adversarial accuracy is something, it's also known as robust accuracy. So what adversarial accuracy basically essentially is that, out of all the points our neural network classifies correctly, of those points, how for each of those points, how many adversarial examples can we generate within a given range? So for example, here we have our L infinity ball, and I've talked about this before. It's basically a range around the point, uh, a bounded but maximum distance range with around the point. And we have a test set containing 100 test set containing 100 examples, and for each of those examples, we have our L infinity bound or L infinity region of size less than 0.3. So the epsilon, the radius, would be less than 0.3 around each point. And we find an adversarial example with a different classification than the original classification, so a misclassification, a different target value, different target label. So we use our PGD attack, and out of the 100 example, 95 of them are classified correctly, and for the 15 of those 95 examples, we find an adversarial example. So then our adversarial accuracy would be 95 minus 15 divided by 100, so 80%. And our test accuracy obviously would be 95 divided by 100. So, 95 divided by 100, so 95%. And
So does everybody understand what an adversarial accuracy means? So whenever you see in a paper and somebody is mentioning the adversarial accuracy, you will always generally see that adversarial accuracy will be lower as compared to the test accuracy, and the entire reason is because it's based on how many adversarial examples could be found, and if there were, then how did the model perform on those, and that's why the adversarial accuracy will generally be lower, and sometimes it can be very, very low as compared, because if you do not have a good defense mechanism, your adversarial accuracy will be can be pretty low if your model is, if your data is prone to a lot of those attacks and your model is not good enough. So when we're talking about adversarial accuracy, we are always looking at both the accuracies. We'll not always, when we're trying to develop an adversarial defense, we just not only look at test accuracy, we also need to consider how your model is doing on adversarial attacks, and that's where the adversarial accuracy plays a role there. Sure, go ahead. Go ahead.
So yeah, exactly. So this is a very important topic of research, and we notice that every time we increase the adversarial accuracy, our test accuracy gets lower, and we're still trying to find the way around it and understand it even better. But this is definitely a very like topic of interest in this field. It always tends to lower the test accuracy every time we raise our adversarial accuracy. So let's look at our defense. So similar to attack, we are also facing our defense as an optimization problem. So our goal here is to find this theta, which you can think of the weights of our neural network. And we want to minimize rho of theta, this value, which is the expected value of this function, the maximum loss. So what this exactly is, we want to find a point x prime within a range Sx, within the range Sx, such that for that point, the loss is maximized. So we want to find the worst case behavior, worst case situation here, and we want to minimize that worst case situation, worst case behavior. D is the underlying distribution of our expected value, and we can pick Sx. Similarly, we pick.
So, just a few clarifications here. You said D is not a distribution of your expected value. D is a distribution of your data points.
Oh, sorry, the underlying distribution of our, sorry, my bad, underlying distribution of our data points. Okay. And we want the expected value of this loss function.
Okay, so what is the rho here? What is that objective function? What are you trying to?
So we're trying to, for each point, we are trying to find the x prime, and for which the loss is maximized. So maximum loss.
Okay, and what is S here? Is there the perturbation?
S is the perturbation region. So let's say L infinity ball, or the region around the region we're interested in, to find adverse examples in that region.
Okay.
Does that make sense?
Yeah, yeah. Okay.
So if this is our region and this is our original x, we're trying to find, say, x prime here, which would, and we're trying to find the maximum loss for a point x prime in this region around our original point x.
Yeah.
And then we want to minimize this loss. If we find the maximum loss, and then we minimize it. You're saying something?
No. Yeah. Go ahead.
So PGD, defense and practice. So even I had some difficulty trying to understand this. I'm not very familiar with optimization algorithms. But what this does is, first we select mini batch B of examples from our dataset D, and then we compute the B max. So by applying PGD, so PGD maximizes the loss, and we find a B max, and that actually computes an approximation. And then from our B max, we accumulate a number of X maxes with the corresponding Y coordinates from our data set of labels B max. And similarly, as we saw on the previous slide, we want to maximize the loss for around the point Sx for every x prime. And here we linearize our inner maximization problem, and we calculate an approximation. And then we use that approximation to solve our outer maximization problem. And here we just update the weights and apply our usual gradient method that we saw in previous lectures. And then we just repeat the process and until we reach a certain number of epochs.
So in this case, Tai, what could be the issues around solving your optimization problem in the second step?
So an over approximation will definitely be an issue. So there's one thing there's 2 points. So one is approximation. So we will discuss this just on the next slide. So this is a major issue, and we wondered that how we will find a good approximate solution to our inner maximization problem we noticed earlier. And how can we be certain that we can find a good approximate solution? Because approximation can lead to us losing a lot of values and whatnot. And with experimentation, we noticed that loss values are usually concentrated around a certain region. And this is in line with why we believe neural network training is possible. So many local minima with similar values. So this is an example. Our goal is to maximize the cross entropy loss measured for 100 random starting points in our region of interest, Sx. The red graph indicates the value of the loss L for an adversarially trained network. So here we see it is very concentrated, but we also know that the loss values are very low, and that's what we would expect. It's an adversarially trained network. And we notice for the blue graph, there's higher variance, but it's still somewhat concentrated in certain areas. So that's why we think we can, and that's like as Purva asked, like what can be issued with the one issue would be like how we can be sure that it's a good approximation or the approximation really works. And this is one point that because these are concentrated, we like there is a chance that we will find a good approximation. But this is still almost an open problem. People are like finding more examples and doing more experiments to like to confirm this. So points to consider when defending. Our model capacity matters. So with larger networks, they're easier to defend, more defendable, and obviously more difficult to attack. Uh, with smaller nets, if we use defense such as PGD, it has significant negative effects on accuracy. So it's definitely not very feasible using PGD, especially on smaller networks. And when training with adversary examples from PGD attacks, PGD tends to perform better than FGSM attacks. So no projection, one step, and PGD is iterative, many steps, and uh, projection. So even on large networks, differences can negatively affect accuracy, as we have been discussing this since the beginning of this set of slides. More research is needed here. This is an open problem. And so by this, we mean that when the robot might be more robust, but it classifies more points incorrectly. So uh, yeah.
There is a lot of also, theoretical research around even model capacity. So model capacity is a very open-ended question and has been there for a very, very long time. How do you theoretically quantify what a model capacity is? So there is a whole notion, there's a whole theory around, people have been using ideas from information theory, from you know where they're trying to quantify and say, okay, my model can learn so much. What is that so much? It's something very vague right now. So if I tell you, okay, I have 5 million images, is that model sufficient? Maybe, maybe not. Right? How do you quantify that? We keep doing all sorts of empirical studies. We do all sorts of random trainings to figure out what that parameter is. But that's something, it's a very important area of research, but it's a lot of theory behind it. So that's something anybody who's interested in theory should always investigate, that because that allows you to quantify things, and it also allows you to understand how the network actually works. And again, yeah, so training with adversarial examples is, as I know Taif mentioned, it's a very, very active area of research. There's a lot of open things. There's no one-stop solution that you can get. We try different things to make sure that we are robust against not only PGD attacks, because PGDs are just one kind of attacks, and there are a wide variety of attacks. So when you're doing adversarial training, or you want to ensure that your model is robust against not only PGD attacks, but a wide variety of attacks. And so it's a big problem in itself, because if you were just to focus on one thing, how PGD attacks is, so you might be able to do something around it. But generally, it's not the case. Generally, your model has to be robust against a wide diversity of attacks. So that's there's an active area, and we should investigate in that. Sure, go ahead, Taif.
Sure.
Any questions, comments from anyone?
Yeah, please.
Everybody is so silent today.
Yeah, question helps everyone.
I think everybody is waiting for the Canada Day to begin. Is that?
No, we're just listening. It's
Okay.
very interesting.
Okay, now then. Okay, good. Carry on, Taif. Let's see.
Okay, so more generally, what we really want is an automated system that can prove the properties of our realistic networks. So it can certify large cyber-physical systems that use neural networks, proving robustness of neural networks. So like proving that adversary attacks aren't possible or less likely, and learning interpretable properties or interpretable aspects, specs of the neural network, like understanding why it does what it does and how it makes its decisions. And it can also help us compare neural networks and see what's the difference between, because there's so many models and it's the same thing. It can give us a lot of information and insight to our systems or models. So we'll begin this problem statement for our automatic verifier. And given a neural network N, we have a property over the inputs phi, and that would be our precondition, and property over the outputs psi, that would be our postcondition. So this would be our statement. So for every input from our domain of inputs I, for every capital I, uh, if our input satisfies the precondition, so this is a satisfaction symbol. If our input satisfies the precondition, uh, this implies that the neural network either holds our property, our postcondition, or returns a violation. We will break this down and investigate this further. So what is phi? Let's define phi formally. So if phi is a region capture is a basically a region. So L infinity ball, we've been discussing the L infinity ball for a while now. We've been talking about it for a while now. So what this region is that around this point, let's say X, and here it's actually classified as 8, this point. And around this, our input X, around these points, we have uh, these possible perturbations. And this L infinity ball is represented here as a hypercube. And within this range, this is how the L infinity ball is defined. Within this range, we want to find all possible perturbations. This region represents all possible perturbations. So all possible adversarial examples where all possible adversarial examples around that region.
Okay, so a question here, Taif. So the question would be, how do you design, or how you think of what could be your L infinity ball or your phi basically? Why are you thinking, so why are they proposing, let's say, a hypercube? Why not any other shape? What is the reason behind it and what it allows you to do?
Okay, so obviously there are multiple ways we can find the multiple methods for finding our region around that point. And in L infinity, there's LP2, LP2 norm, and L infinity norm is used most frequently. It's because it takes the maximum distance between the points that define similarities, similar behaviors. So it takes the maximum distance between the points around it that have similar behaviors, if that makes sense. We have LP2 norm, which takes, I think, the square, and it ends up being a Euclidean distance. This is we believe the L infinity norm is one of the ones that capture most of the properties, that it takes most of the points and the properties, and are usually yeah, please go on. Go ahead.
So
I was just
what?
wondering.
Why?
Okay, go ahead, please.
No, you go ahead. Yeah, I can wait.
Yeah, I was just wondering because it looks like a cube, and you said that all the points around the 8 looks like an 8. So when you say has similar property, all the points around in the hypercube, do you mean that similar property to a human observer or to a computer, right?
Yeah,
Because because after all, you are trying to. Oh, we are concerned about the hypercube because the machine learning model is not able to. Is fooled by some of these examples, and in order to make it robust, basically what it looks like what you are suggesting is that you have a point, take all the points around it inside a hypercube, train the neural network with all these points so that the model is robust. Is that right? Or I'm totally confused about it.
okay, for sure. So what I'm trying to say is we we take those points and see for which points we can find an adversarial example for which the neural network will classify classify the point wrong, but the actual label of the so the actual label would be correct. So we know the actual labels of the points we're talking about, and those points we see if their neural network actually misclassifies those points by adding a little perturbation. We see if the neural network actually misclassifies those points.
So I think, Taif, you should do one more thing. So go back to your previous slide, I think. I think you went pretty quick from defense to verification. And I think that's where the problem is. So now he's not developing a defense mechanism. What he's doing is he's doing a verification. So verification problem says, I'm given a model and I'm given a property that models should satisfy. You want to ensure whether your model actually does meet those requirements or does not meet those requirements. That's what a verification problem means in general. So for example, let's say, let me give a more simple example in real world. So let's say you have a car, and I always give examples of cars, but those are easy and easy to understand. So now you say, if I have a car and the property says I can only fit in 4 people in the car, so that's a property of a car, and there's a function that defines the fact that, okay, let's see if it can fit 4 people. And once you start putting people in and then say, hey, I can fit in 4 people, but can you, that's a property has been met, so that's a good thing. If the property doesn't hold true, that means you're not able to fit 4 people, you're only able to fit 3 people, your model should tell you cannot fit more than 3 people, or instead of saying, okay, you may be able, it doesn't give an answer, or it gives an answer, maybe you are able to fit 4 people. So a verification problem is designed in a way that you tell either you can do this correctly. If you cannot do this correctly, you tell that you cannot do this correctly, or you give a counter example saying that, hey, this is an adversarial example because if you make this perturbation in this input, it's actually an adversarial example, although it looks similar. Am I correct, Taif?
Yeah, absolutely.
So here he's not doing a defense, he's just doing a verification. He's solving a verification problem. So a verification problem for a neural network. Now, in a neural network setting, it's saying, okay, neural network is a model, it's a black box, you don't know what it does, but it does something. And now the fact is, what you want to say, there's a set of properties you define over your inputs, and you want to ensure, and you define some properties over your output, and then you check whether your neural network the output from your neural network meets those output properties. Is that correct?
And those properties are the preconditions.
So there are properties over the input and there are properties over the outputs too. The preconditions and postconditions. So there, and now what he's defining at the moment is the properties over the inputs. So so for the first thing is to define these properties over the inputs, and that's what he's trying to do. Now, the question for Taif should be, how are you coming up with these properties? What is the intuition behind coming with the property that you were presenting?
Okay, sure. So here let's define our properties, so our precondition phi more formally. So for example, here we are trying to capture a brightening attack. So and we keep some of the values as they originally were, and we change some of the other values with some symbolic epsilon. Symbolic values, these are not necessary for we'll look at what these really mean later on, but these are relaxation values for approximations.
No, you're still going too complex, Taif. You have to bring it simple so people who don't know exactly what you're trying to say. So what do you mean by the properties of an input? So when you say, now you give an example of a brightening attack, what does it mean to be a brightening attack?
So the pixels.
Right.
We are playing with the pixel intensity. We are seeing what and around the region, which pixels have similar intensities. And that would be an example.
Right.
That would be a property, yeah.
That's right. So a property would be saying that the pixel values so let's say I take a pixel and the neighboring pixel should have a similar intensity levels. And that's what a property of an input would be. But there's a brightening attack, it might be likely that the neighboring pixels may have a highly varying pixel intensity values as compared to some values, and that it may be an attack, it may be a normal thing in the image, but that's a property that you define. That what are you looking for in the pixel values in an image that will look like an attack? So that will be a property that you are interested in. In this case, I will say, okay, my pixel values should be within this range because I'm interested in, if they are within this range, everything is good. Okay. Does it make it more clear? Abhijit, do you want to add something?
Yeah, I think it's clear now. Yeah.
Okay. Anyone else? Okay, good. Go ahead, Taita.
So one issue we have here is that so for pixel, if you're considering pixels, there we have two values, and here the region gets quite large. 784 points. So if 2 to the power 784, that's a very large number. That's a challenge we have with our region, and we will be looking at that challenge. So I hope this region part makes some sense now. So let's define our property, what the property actually is. So here we say our property is that every point classifies, so this is our output property, so our post condition. So every point classifies to 3. So that's what we want. We want around our original point, we want to classify, that would be our output as we are training, as we are trying to make it more robust. We want all the points around it to also classify it as 3. So for all values between 0 to 9, the probability of it being 3 should be larger than probability of it being any other number. So 0 or O here is the output layer, just before the softmax, last softmax. And again, we want the probability of it being 3 higher than it being any other number. So we want every point around in our zone in our cube to classify as 3. So this will stop for like adversary attacks. So for people to attack our system, we're trying to make it more robust. I hope that makes some sense. So how do we prove this property? Our region here could be unbounded and even bounded, but very large number of values, very large number of inputs or points, and it's almost impossible. So as I mentioned before, 2 to the power 784, it's almost impossible to enumerate through each of those points and check if each of those points satisfies our post condition, our psi. So, and the question is that how do we challenge, like how do we attack this challenge? So before going into that, there's these two terms. We need to define. So a certification method is called complete if it is able to prove the property holds when it actually does hold. So it can tell you it can prove the property holds when it can tell you the property holds when it's actually true that it holds, and it's called incomplete. A certification method is called incomplete if it cannot guarantee that it can prove a property which actually holds. So if it cannot completely guarantee, say if it says that the property doesn't hold, it's not guaranteed that property does not hold. And so we will touch on the incomplete methods and see how this sort of works. So we will investigate a specific type of incomplete method based on bound propagation through the neural network. So starting with our initial precondition phi, we will push it through the neural network, push the region through the neural network, and we'll compute an over approximation of the effect of each layer. So our region is so big, the only way we can really deal with it is making an over approximation of that region, at least approximation of that region. So make it smaller as possible. Then we can finally enumerate through the region and see if it satisfies our post condition psi. So let's see how we could prove our example with property with this example. So compute bounds by propagating our region phi. So we take our region and we put it through these transformers, these are the layers, and we put it through the layers, we put it through the first layer, and we get a convex approximation. This approximation is achieved
So,
through,
Five, can I interrupt? Sorry.
please.
So basically, what he is trying to do here is, in a standard neural network, you would be feeding in input numbers, and those numbers get propagated forward through a rectified linear unit. Then you do softmax, you do pooling, you do all sorts of things. In this case, it's more of a symbolic representation. The numbers are actually not being propagated. What is being propagated are these symbolic functions that he has designed, that he has shown there. So for example, and the first thing that he shows here is at the bottom left, this region that he has designed, the region phi, that actually gets propagated through the network. It's not the numbers. So you're not feeding in the image as is. You're feeding in these symbolic equations. There are symbolic regions, or there are regions, I would say, that get that propagated through the neural network. And so one needs to really, I think you need to take one step back for everyone else also to show how do these regions actually propagate through a neural network through an example, because otherwise it's going to be too overwhelming for everyone and might be too complicated.
So that is what the entire next lecture, honestly, most of this course is about. So
Right.
like all the next lectures, we will see how we do this convex approximations and all different kind of convex approximations. Those like
So,
many lectures just go on talking about that.
exactly. And so for example, quite a few people would have never seen what a symbolic representation would look like.
Even
Right?
yeah.
Exactly. So you want to try to make it more simple in the sense of everybody understands exactly what does it mean when you say region phi. Show it with an example with just 2 equations or 3 equations. How would that region look like? What does it mean to say that region in a 2-dimensional space, right, or on a 3-dimensional space? You start doing by those examples, and that will allow everyone to follow through and move on. And and then you say, okay, when I give, so for example, that region can be a ball, for example, or you said a hypercube, right? Now when you do a transformation on that hypercube, what happens? It changes into a different polygon depending upon what the weights of the network are, and how does those transformations happen. And that's what should be. So maybe at every step we should have some examples for everyone to understand, because given that not everybody has a background, it will be challenging for to understand and follow through. And I think this is the foundation of all what they've done in the course, so it might be worthwhile to put in that effort.
Yeah, for sure. I will definitely, because even I
Yep.
don't understand these
Right.
well enough, so it would be hard for me to fully come up with concrete examples. They do go through a lot of examples right now. I'm obviously just following the lecture right now. They're trying
Right.
to give a slight idea of what's going on, and then they break it into, they're starting with like smaller similar
Correct.
things, and they like start with more examples and more bigger.
Yeah.
But yeah.
No, good. No, that's fine. So yeah, I think that's fair enough. However, today I will have to leave in like 1 minute now because I have another meeting at 11. But I think we should stop at this point, Taif, and continue on this in the next lecture, because I think this is you're starting a whole complex idea here. So I think let everybody absorb what you talked about and
Sure.
share the presentations. I think everybody has the link to the course, but I think it's good for everyone to just look at it also yourselves so that you get a sense of what's happening. And in the next lecture, we'll continue on from here, and maybe by then Taif should be able to come up with some examples. And it's not only Taif, by the way. So if anybody, you guys can get together on virtually for now, and try to, let's see, one second. Let me do this. Get together virtually. For example, Abhijit is very comfortable so far with this concept. Devansh is a senior person. He knows quite a bit of these things. So why don't you guys get together to design those concrete examples, and sometimes it's always good to learn with peers, and then come back and again explain it, because I think you have to be giving a tutorial, right? So you want to make sure we know every damn detail of this whole topic.
Agreed.
Does it make sense?
Yeah, of course. Yeah, that would be great, honestly.
Yeah. And so and you guys are a part of the group, so just ping each other. I don't need to say, hey, guys, come and talk to each other. You can talk whenever you want. It's a free thing. I know it's a weird in this virtual environment, but still, let's assume that everybody is available all the time. Just ping them, and let's make it happen that way. And hopefully, in a few months, we will be on campus. So I think with that, I will stop now because I need to leave. But if anybody has any other pressing questions. Okay, if not, then thank you so much, guys. And I need to leave, but we'll see next week. And Taif, are you going to continue next week?
Yeah, sure.
Okay, sounds good then. Thank you so much, guys.
Thank you. Yeah.
Thank you, Taif.
Thanks.
Thanks, Taif.
Thanks.